I'm very sure I'm not recording.
Okay, it just came.
Yeah, I've started recording long ago. Maybe you just saw it. All right. So statistics for management science and analytics, we are looking at conditional probability. Now, the last time that we have met, we have looked at the screen. I've changed the screen. Is it showing? I just changed the slide of the screen. Is it showing?
It's showing now.
Yes, it is.
So, what we did is we looked at the different kinds of probability. We looked at a lot of the basics of probability. And I know that you've gone through the experiment, the event, the definition of probability, the final samples, counting methods, and you guys can confirm that you went through the combinatorial methods and the multinomial coefficients, right? I want to believe that. You've done that. You've gone through mutually exclusive and non-mutually exclusive, distributive, De Morgan's associative probability. You've done all of those things. The actual definition of probability, the theorems, we've looked at it, the inequalities associated with it, and then the counting, which includes permutations and combinations.
Yes, that's where we ended.
So what we want to look at today is conditional probability. We'll look at Bayesian theory. Now, if there is time, I don't think there'll be time, we'll look at independent and parallel series systems. And the exercise, we'll do it here. And you will also, I'll actually give you 2 homeworks and we shall do 2 class tests. So feel free and be asking questions as we go. So let's start with conditional probability. Just to break things down, give me another word for conditional. Conditional here is being used as an adjective. Give me another word for conditional. Albert.
So conditional would be based on circumstance.
Would be what?
Circumstance.
Circumstance. Okay. It is not so much of a strong way of looking at conditional. Who else?
Contingent.
What's the name of the other guy?
No, Jerry, contingent.
Jerry, are you talking?
Yes, I said contingent.
Oh, hold on. I think I've muted myself.
No,
are you talking, Jerry?
Yes, please.
Hold on. It looks like. Can you hear me?
Yes, Doc, we can hear you.
Yes, Doc.
Good. There you go. Ahead. I think I wasn't hearing you.
Contingent.
Contingent. Okay. Emily, which other word do you have in mind representing conditional?
Doc, I'll say given.
Given. Yeah.
Yes.
Given. Okay. Holding something constant. Okay. Conditional has to do with things related to dependent, given, contingent. Now, one of you is having some bit of noisy background. I don't know which one. I think it's gone now. But if you sense that there's some bit of noisy background, then you mute yourself. Okay, so what is a conditional probability? We have 2 events, event A and event B. The conditional probability of this event A given B, that is, given that B has already occurred, is denoted as P of A given B, or P of A with a vertical sign B. The vertical sign indicates that the B has been given, or the B event has already happened. The conditional probability is given as the probability of A conditioned on B, or probability of A happening given that B has already happened. This is expressed as the probability of A intersection B and its intersection, or is plus and union. So note some of those things. So it is a probability of A intersection B relative to the probability of B. This is what is known as the conditional probability of A given B, or the conditional probability of A and B. So look at this function, because we are going to manipulate it in so many ways. From this function, we note that the intersection here, if I should do a cross multiplication between this and that, we can now say that the multiplication of probability of A given B multiplied by probability of B should all be equal to that at the top. Which means that the A intersection B is the probability of A given B multiplied by the probability of B. But also, because the probability of A intersection B is A given B multiplied by B, it is also B given A multiplied by A. Look at this. If you don't understand, you ask. You have to fully understand this before you see the test. No question. Are you clear, Albert, so far? Are you clear, Albert?
Yes.
Okay. Now, if A and B are disjoint, then the probability of A given B is 0. Who can tell me why? Emily.
Doc, because the intersection of A and B will be an asset.
Yeah. And therefore, so my question is, so why is the conditional probability of A and B, or A given B, why is it 0?
That because
You started because and you stuck. Or it is we who cannot hear you. You hear?
sorry. Yes, Doc, I can hear you. Okay, I was saying it's because if B happens, then it means A cannot happen. And if A happens, then B cannot happen. So it's going to be equal to 0.
So who can tell me the relationship between the conditional probability and then the joint probability? Albert.
So I'd assume that
Did you understand my question? Did you understand my question?
That what is
I said, what is the difference between the conditional probability and the joint probability?
The difference between them, I can't tell for now.
The connection. Yeah, that's why I was asking you not to talk quickly until you have understood the question. Let's go to Jerry. Which one is a subset of the other? Jerry, are you there? Jerry.
Doc.
Where were you that I had to call you twice?
Doc, I'm here. The disjoint is a subset of the conditional.
Why? It's like asking somebody, what is 1 + 1? He says 2. Okay, tell me why. Oh, yeah, why? Go ahead.
But in both situations, situations use contingency measures or given measures.
Okay. Yes, Emily. Emily, are you here?
Yes, Doc.
Guys, when you don't know the answer, just say that no idea. When you guys keep quiet, I'm not so sure whether you could hear me or you are thinking about it. Are you with
Please,
me?
the question is not that clear.
Good. The question is that what is the relationship between the conditional probability and the joint probability? You know both of them, right?
Yes, the joint probability is when
No, don't tell me, don't tell me, don't tell me. I didn't say tell me. I say you know both of them, right?
Yes, Doc.
Good. Now that you know both of them, tell me the difference or the relationship between them. That's my question.
Okay, so Doc, I would say the conditional probability is a subset of the joint probability because the conditional is just a small portion of the joint that's telling you what would happen if you are
Please hold on a
relying on
second.
the
Yeah, please go on, Emily.
Okay, so the joint combines the two sets, whilst the conditional is just looking at a portion of the set that is being affected by the other set.
Are you sure?
That's what I think.
Both events occur together when you're looking at joint. If you have the joint probability of A and B, both of them occur together. When you look at a conditional probability, okay, one event occurs given the other. But then the joint probability both happen at the same time. But then the conditional one occurs after the other has occurred. Are you guys with me so far?
Yes.
Yes, Doc.
Okay, how are you with me? Jerry? Who said yes?
So, Doc,
No, you said the joint probability both occur together.
Mm-hmm.
The joint probability both occur together, and the conditional one occur given the
Give me
other.
a practical situation in life that match what you just said. The same situation, but that relates to this. Okay, so you can have two matches being played at the same time. Man United is playing Chelsea, and at the same time, you have Liverpool is playing Tottenham. They all started at 2 p.m. They are all finishing after 90 minutes. Is that joint or conditional?
Joint.
Joint.
After Man United has played Chelsea, then you have Aston Villa playing Tottenham. It happened after this match had finished, 2 p.m. from 2 p.m. to 4 p.m. Then this one began. Conditional or joint?
Conditional.
Okay, so in that case, then it appears that the two are not related, isn't it? Is that it? No. Watch yeah, it appears, but it is not. It is not because the joint probability is the probability of the intersection of A and B, isn't it? So if I were to, we'll come back to that today. So the joint probability is the probability of the intersection of A and B. This is joint. And the conditional probability is the probability of A giving B. But I've not told you the equal to what they mean. Because of the right-hand side of the joint probability, what you have on the right here is this one. This is a joint probability. What you have on the right-hand side of the joint probability is actually P, A giving B, okay, multiplied by the probability of B. So the joint probability is actually the conditional probability, okay, multiplying the second event. The probability of the condition or the conditional probability of A given B multiplied by the probability of B, the second event. And this one, that is actually this. So the joint, the conditional probability, this very one here, It is also the probability of A intersection B giving the probability of B. So both of them are defined in terms of the probability of B, but one is multiplying, whereas the other is dividing.
Dividing.
Understand this before you see a test. I know you understood it when I said that one is when you are dealing with both happening at the same time. But the other is when you are dealing with one happening after the other. They're both happening, it means a portion of the both are not happening. Do you agree with that? They're both happening, A and B here. Okay, if I say this one is 1, 2, 3, where is the joint probability?
2.
2. So it means that there are some portions of the event that are not part of the joint probability. You agree with that?
Yes.
Keep that in
Yes.
mind. There are some portions that are not part. But then when you look at the conditional probability, you have that 2. Okay? But at the same time, you have that of the probability of B. And if this one is B and this one is A, okay, then the joint probability is 2, but then the conditional probability is taking not only the 2, but it's also doing something with the 2 plus the 2 and 3. Does it make sense?
Yeah.
Do you realize that the probability of B is 2 and 3?
Yes.
Yes.
So you can see that the conditional probability has more information than the joint probability.
Yes.
Are you clear? Do you get it? Keep that in mind.
That's clear. Yes.
Okay. I had to go further for you to capture this before we go on. That's what I know. All right. So this is under the assumption that the situations are joint. But if they are disjoint, then the conditional probability is an empty set. Okay, let's move on. Okay, hold on. Because ideally, I wanted you to try this rather. I don't know why. All my animations have vanished. Can't believe it. Just a second, let me be sure. That's animations have vanished and they shouldn't have. It's a shame. Just be sure that this is. Let's move on. So this is an exercise I want you to do. You do a lot of proofs, so I'm giving you some of these proofs. Then I'll let you do some proofs yourself. Show that for event A, B, and C, where C is a positive value, okay, the probability of A union B given C is the same as the probability of A given C. And watch the words because you're going to appreciate this in your next test. I'll show you later. The probability of A given C plus the probability of B given C minus the intersection of A and B given C. Now watch it. In all of them, you have given C, given C, given C. And I've already said that C is positive. So the union of A and B given C is actually the probability of A given C, B given C, and then the subtraction of the intersections. If you were to draw a circle, A, B, and then C, 1, 2, 3. The union of A, let me add 4, 5, 6. The union of A and B, if there was no C, what would it have been?
That would have been P of A plus P of B minus P of A intersection B.
So using this diagram, it would have been what element?
Okay, so it would have been P of A, which is 1, 2, 4, 5, plus P of B, which is 3, 2, 5, 6, then minus 5, 2.
But you're talking beautifully plenty. But looking at a Venn diagram, you could have said it easily. What is it?
That would have been 1, 4, 3, 6. 1, 4, 3, 6, 2, 5. Look, it will be the whole A and B.
Exactly.
Yeah.
It will be everything. It will be what I have labeled. And there was a reason why I didn't label that of the, exactly C. I didn't label exactly C. Yeah. So if there was no C, that is what the situation would have been. Now, the A union B giving C is the formula that you see here is the probability of A giving C. Now, why is A giving C? What are the elements? Albert.
4, 5.
A giving C.
A given C. So when C happens, 5 and 4 happen.
So what are the elements? Again.
4, 5.
Good. What is B giving C? Albert. I'm sorry, Jerry. Jerry. See, he will wait and then he will say that.
No, 5, 6. 5, 6.
What is
No, 5,
A?
6. Hey.
Okay. What is A giving B? A intersection B giving C?
Log 5. It's 5.
Good. Now this 5 will have to be taken out. And if you're taking the 5 out, then the union of A and B giving C is what?
And B given C will be 4 and 6.
Sorry?
4 and 6.
Now, I didn't say you should take 5 out as it is here. I was only taking the intersection. Okay. What is A intersection B? Giving C.
It's
5.
So what is A union B giving C?
It will be 4, 5, 6.
Yeah.
Exactly. To be 4, 5, 6. So keep that in mind. Okay.
Yeah.
Now let's go back here. I'm now taking it back to the proof. So the conditional probability of an event, let's say an event is E, given C is given as this. So the probability of event E given C is the intersection of B, E, and C divided by the probability of C. Now watch it. The last item that you see here, very important, they are the given. Okay? They are the given, the C. Okay? And that is also the one on the right of the numerator. So we know that this is the definition of the conditional probability. Please note, this is the definition of conditional probability. It's not the definition of Bayesian theorem. Okay. Now, we are proving that this very element is equal to this minus the intersection. So we start from this same one. We can prove that A union B given C from this extension here, from this very one that we just did here. Let me just go back. Okay. From this very thing that you see here, we can write the conditional probability for this. Look at it. I wrote probability of E given C as that. So I can say that the probability of AUB given C is the intersection of the probability of AUB and that of C, the same numerator. Do you understand this part? Using the conditional definition. Jerry.
Yes, Doc.
Good.
oh.
Now you divide that by C, because remember, according to the conditional definition, we have C here. So you have C. Now you can split them, because it is, look, if you look at the top part, the A union B is A union B separates its intersection with C. And because it is its intersection with C, we can now take this and do this A here, okay, its union with C. Then B here, its union, sorry, its union, its intersection. Okay, because there's an intersection. Okay, this A here is intersection with C, and this B here is intersection with C, and then we can unionize the two of them. And that is what you have at the top here. I'm sure you understand this. The
Yes,
property that is operative here is a distributive property. And then, of course, all divided by that. Remember, we are proving towards the end, we are proving that what you have on this left-hand side is equal to the one on the right-hand side. Now, from this distributive property, we can now conclude that the A union B, watch here carefully, okay, from here, we can say that the intersection of A and C, which is the first part, okay, plus that of the intersection of B and C, which is also this part. Now, we say plus because it's a union, okay? But because anytime you are dealing with union, that inclusion-exclusion principle of union of events, in this case, we are assuming that the two events are not what? For you to be able to capture what I'm doing. We are assuming that the two events are not what? Are not joint.
Joint.
Isn't it? They are not joint.
Yes.
That's why we are taking off the intersections. So watch it here. You take the probability of A intersection C, which is this, plus, because we are talking about union, the probability of B intersection that. Then you take out, if these two events was just A and B, you would just take out the probability of A intersection B. But this one, it is not that. You are rather taking up the probability of A intersection B is intersection with C. And that is why this part here will have to be excluded. Now, if I were to exclude this part here, okay, then it is under assumption that the two events, or the three events in this context, okay, are not joint events. So we can proceed further and say that from here, you can just break them down, divide both sides by P, the probability of C. So each one will be divided by the probability of C. The second element will be divided by the probability of C. The third element will be divided by the probability of C. And at this stage, do you guys sense something? Do you realize something? Because from the conditional probability, again, we can rearrange this. Do you realize that?
Yes.
Look at this from the conditional probability here.
Yes.
Rearrangement will be like what?
So the first one will be probability of A given C.
Exactly.
Plus probability of B given C.
So we are taking this one backward. So this one will be probability of A given C, probability of B given C, and then the last one will be the probability of A intersection B given C. That is the proof. And this becomes the final proof of that. So we've been able to prove that the probability of A union B given C is actually the whole of this right-hand side, moving down here. I could have given this to you as a test, but I said to myself that example one, I wouldn't want you to do that. But you would have been able to do, wouldn't you, Alex?
For the first instance, no, it would have given me too long.
Then, if you don't understand this, ask before we go to the next one.
This I understand.
Emily, is it clear?
Doc is clear. Yes, Doc.
Now, if A and B are disjoint, what would have been the answer to this?
Doc, there will be no need for the minus part.
Yes, the intersection and the, okay.
Exactly. So there wouldn't be any need for the minus part. Okay, let's move on. Now, still following on the principle of conditional probability here, you would notice that this event, the event probability of A complement giving B, is actually 1 minus the probability of A giving B. I'm sure you know that, because the probability of A giving B plus the probability of A complement giving B is 1.
Yes.
Okay. Well, that's what I just said here. Okay. So you can now add these two. So any event and its complement, it doesn't matter. Okay. Both of them are still giving whatever. Okay. One is giving B, the other is also giving B. Okay. The sum of the probabilities will be equal to 1. Okay. Which means that the probability of B giving B is also 1. Now, who can tell me why the probability of B giving B is 1?
I mean, it's a certainty. So if something is likely to happen based on itself, then
I'm talking about practically. Why that makes sense? Why is the probability of B giving B equals 1?
So are you please respectfully, are we to prove that
You are
or
not
we should give example?
explaining why that is so.
Okay, so probability of B giving B is the same as probability of B intersection B over probability of B. And probability of B intersection B is the same as probability of B times B all over B. Everything cancels out and gives you 1.
But I hope you'll be able to do the test then. So that holds. If that holds, then the general situation is this, that the probability of A giving the B complement is not the same as 1 minus the probability of A giving B, just as the previous one is. Take note, because the probability of A complement giving B is not the same as the probability of A giving B complement. It's not the same. So you can't say that proves that. And if that doesn't hold, then obviously, then this doesn't hold, and obviously, this also doesn't hold. I mean, it's not true. Not that it doesn't hold. It holds that it's not true. Any question? You're about to do your first test. Any question?
Doc, please, before that, can you go over why the probability of B giving B is equal to 1?
I don't know. This guy was just going through.
Yeah, Doc, how he explained it is the one that confused me.
Okay. So, Maza, see, I told you that there's one thing you can know, and how you can convey that knowledge is different. You know that, Jerry?
Yes, Doc. Yes, Doc. He said it.
The ability to convey knowledge is different from having the knowledge.
Yes, please.
If you tell me that B says that it rains today, okay? If we already know that it's raining today, then we can say that the probability that it rains today, given it rains today, is 1. I want to repeat that. So let's say that we say that let us have B today. It rains today. If we already know that it is raining today, watch the word though. I'm using a continuous tense verb. If we already know that it's raining today, then we can say that the probability that it rains today, given that it rains today, is 1. Because given that it's raining, then the chance that it's raining is certain. Jerry, can you explain with your words a simple way to see whether she'll get up?
No. It also end up the proof that I did. I think she said she didn't get that one. I was using the mathematical way to explain that.
Now I'm using the practical way. So start with your mathematical way for it.
So probability of B given B is the same as is equal to probability of B intersection B over B. I mean, is that okay with that?
The probability that Emily is in this class, given that Emily is already in this class, is 1.
Yes. Okay.
Because she's already in the class. And the probability that she's already in the class, because the probability end up in 1. So the complement of Emily is in this class is that Emily is not in this class. But then the probability that Emily is in this class, given that Emily is already in the class, is 1. Because that matches the fact that when you go and find the fact that Emily is not in this class, you will not find anything for Emily is not in this class, because that Emily is not in this class is going to be 0. Because there is a condition that Emily is already in the class. Does it make sense?
Yes, Doc.
Okay. So we're going to do some quick work. I decided to give some common definitions so that you all use that. So let's look at this. I'll give you an interpretation to this before we start. You have a box and it has 4 red balls and 2 green balls. You're about to draw from the box 2 balls without replacement. And you're going to check the color. So you close your eyes. Right now, how many balls are in the box? How many balls?
6 balls.
6 balls. Keep that in mind. So you got 6 balls now in the box. You close your eyes, and then you try to pick a ball from the box. Then you check the color. Before we ask you the question, what shows that this question is a conditional probability question? There are some 2 things that shows that it's a conditional probability question. Albert, give me one.
So the first is that without replacement.
Good. Explain to what extent that without replacement shows that it's a conditional probability.
So it means that if you take the first ball out, if you don't put it back, the subsequent draws will not be the same as the previous draw.
You mean when you say will not be at the same, you mean it will affect the probability?
Yes, it will affect the probability of the
Why are you saying it will affect? What has happened in the box?
Because the sample space has reduced. So
good. The content has changed.
Yeah.
Good. So that's a first good point today. The second one, Emily. What is the second thing in the sentence that gives the impression, it's a word, that gives the impression that this is a conditional probability?
Successively, draw successively 2 balls.
One word.
Successively.
Successively. Why? You're right. Why do you think that word creates an idealism of conditional probability?
That was you're going to be taking it one after the other, not at the same time.
So
what you pick the first time will affect will affect the probability for the second one.
So the both of them create that knowledge. Okay. And that, see, you got to be able to discern that a question carries an idea of conditional probability before you can even think that it has an idea of joint probability. because now we know the connection between. Before you can now even understand the Bayesian theorem between the three of them. So the dependency here is critical. The dependency here is the hallmark of conditional probability. Okay, so now we know what makes this thing a conditional probability question. The question now is, find the probability that the second ball is green. Now, before you can do that, there are a couple of things you need to negotiate your mind. First, you need to define some event. So I've decided to define the event for you. Let G1 be the event that the first ball is green. Let G2 be the event that the second ball is green. Now, why do you think I didn't talk about G3? Jerry?
Because we are drawing two. We are drawing two balls.
Exactly. Even though there are how many balls?
Even though there are 6 balls.
Good. So that is why we ended at 2. Now, R1, let that be the event that the first ball is red. And R2 should be the red ball on the second ball. Emily, why did I end with just R1 and R2 and not R3 and R4?
Because we are drawing just 2 balls.
Okay. Now, I want each one of you to calculate, and you should have it on a paper now. Okay, have your ID and everything. Calculate the probability that the first ball is red. And I've shown you a representation of that.
Mm-hmm.
Please, you send me this thing. You can send it to me by WhatsApp. You can send it to me by picture. You can send it to me by private chat here. Anyone. I'll hold it. You have just 30 seconds to give me. Let me see. Okay, just 1 hour. Hey, 1 hour. Just 1 minute. It shouldn't take you more than even a 30 seconds because the real ones are coming.
Do we send this one or we should finish everything before we send?
No. It's just one question I've just asked you. So
okay.
send it. If you have your answer, you can send me your answer privately so that you add up to the rest. But I need the answer. You can send it here on this chat. You can send it by WhatsApp private chat, or you can send it by taking a picture, either one. So far, none of you have sent to me. You still have 1 minute. You're still within the 1 minute. All right, it's time. Anybody who hasn't sent, I'll mark it down. Take note. So I have the answer for only Albert.
I've sent it to you.
You sent it after the document. Jerry, you haven't sent anything at all, isn't it?
Right now, I'm taking it. I'm taking the picture.
You're not supposed to take it. It's just type the answer.
Oh, sorry.
Type the answer. What's up the answer to me?
Okay.
And next time, don't delete again.
Yes, please.
Okay.
I'm typing right away.
You will write your everything in your book. You give me that one later. But
Yes,
And
please.
this the final answer quickly. Albert, I know you've sent it in the chat here, which is fine. But are you able to also WhatsApp it to me?
Yes, please.
Please, I'll send it. Oh, privately.
Also, if you have sent it, I will know. So until I mention it to you, don't say it. Because there's nothing you have sent. Albert, what have you sent me? Your name?
No, I was just in case you didn't know who was sending a message. Yes.
Oh, okay. The only person left is Jerry.
Please, I've sent it.
On the WhatsApp?
Yes, on the chat, on the Zoom chat.
You can't send it on WhatsApp.
Okay, let me send it right away.
And always use that means, because that means I can always keep it. You're delaying that. You're holding everybody ransom.
Look, this, I'm sorry. Like this, I have sent it now.
All right, good.
Yes.
Now I have all of you your answers. So
Look,
now
sent it.
check the answer to this question. And I think two of you got it right. Your answer is 4/6. Why? Or 2/3. Why? And by the way, those of you who gave me the answer in decimals, next time I need it in fractions, okay?
Yes, please.
And I don't have a problem whether you break it down to 2/3 or you keep it as 2/6. It doesn't matter. It gives us the same value. But I always keep it in fractions. So why is this so? Emily, explain quickly.
That's because there are 4 balls and the total number of balls are 6. So the probability of drawing a red ball the first try is going to be 4/6.
Why is it 4? Why is it
That's
numerator?
because out of the 6 balls that you have, there are 4 of them are red. And so the probability of picking one is going to be 4 out of 6.
All right. So this is the easiest of all the questions out of the 12 questions. Let's continue. I want you to find the probability of R2 that a ball selected at random with a replacement is, what is the value? Also find the probability of green one, a gene one, and that of gene two. Now you have 3 minutes to do that. This time is already set.
Please, probability that the second ball is red.
Okay.
Said the
Yeah.
probability that the second ball is red.
Yeah. Remember, we are still applying with and without, without replacement. About 50 seconds for all. You're giving me R2, but you're not giving me the rest. You have to find R2, PG1, PG2. Oh, the other.
Okay.
I didn't know that you have to find all three of them.
No, Doc, sorry.
But you're not looking on my screen.
I'm looking on your screen. Wait, that was just the first one.
Albert, you have not given any answer.
Sorry, Doc, I was just typing.
Your 3 minutes are gone. It's getting to 4 minutes. Jerry.
Oh,
You're giving me one answer.
yes, please.
All right. So, Albert, you finished everything. Emily, you've given all, right?
Yes, Doc.
But this thing is not clear at all. Next time, check the camera speed. So, all right. So that's it. Let's stop it. So the first question, and then we have a second question, and then we have a third question. Now, the first one, as you all know, was the probability that the first ball drawn at random was red. That was the first question. And we were able to prove that that first question gave us a value of what? Emily, you saw 2/3 or 4/6. That was what I gave you. 2 of you got it right. 1 of you got it wrong. Is that one correct? Okay. So 1 of you got it wrong. Then the next one is to find the probability that the second ball is red. How would you work it that one? The probability that the second ball is red. Well, that's fairly simple. Why? Because you see, the probability of a red ball on the second draw is going to be 4/6. You'll be tempted to think otherwise, but it's going to be 4/6. Who can tell me why? One of you wrote, what did you write? 3/5. The other person, I mean, you know yourselves. The other person wrote half. And then the other person, Emily, your answers are 2 different answers.
But I was saying that since we are looking at the second ball, I was saying if the first ball was green, then the probability will be 4/5. But if the first ball was red, it will be 3/5. That's what I wrote.
Oh, did I? Okay, hold on. I think it's my mistake because I made the assumption that it is
Without replacement.
Yeah. I should have made the assumption that it is without replacement. Okay, so that's right. Just a second. Let me see. Yeah. So the first one we did it. It was 2/3. Okay.
Yes.
And then the R2 is also 2/3. Which one of you got it? Without replacement. Oh no. R2 is 2.
Without replacement.
Oh wait. There's my R2. R2 is 1/3. Hold on, no. R2 is 2/3, which is the same as R1. It doesn't change because it's expected without replacement. Which of you got it?
If it's without replacement,
doesn't it mean that the
if it's without replacement, doesn't it mean that it will reduce?
Sorry?
Because this is the second draw, meaning that one has already been taken out.
Yeah, but I've also not indicated that it's conditional. I didn't say you should find conditional probability. I didn't say find R1 giving R2. I didn't give you conditional probability. I was only telling you to find a simple probability. This is a simple probability that you're supposed to find. If it was a conditional probability, yes. But this is a simple probability. So in a simple case, I want to get a second draw. It has nothing to do with whether or not there is.
The question was 2 successive draws. Getting the second ball is already getting the first one.
First ball.
So what is it? Ben Susan?
Yes, let's go.
Let me see. Ben Susan had 3/5 because you're looking at without replacement, right?
Yes, please.
Emily had 4/5. So Emily, why did you?
That I was saying I gave 2 answers: 4/5 if the first ball was green, and then 3/5 if the first ball was red.
Yeah, but then you are told to only find for the red.
Yes, Doc. So they are both the probability for the R2, the second ball being red, but they are okay. Maybe I understood the question wrong.
Yeah, I think that is because of the way I have structured the question. That is why it might not make clearer sense. That's why you guys are reading a lot of the replacement and without replacement. But remember that with replacement or without replacement, once you bring that into the picture, it's on condition. It's on conditional way. But I've not come to the conditional probabilities yet. If I had said that conditioned on the fact that you are taking the first ball. Okay. But if you look at the way I wrote it, okay, if I want to write it, I would have actually written something like this. I would have written probability of R1 giving R2. Okay, or probability of R2 giving R1. Okay, so then you know that I'm dealing with conditions. But I wasn't dealing with conditions. I was dealing with how they are. How they are. Without condition. Yes, it is without replacement and observing the color. But remember that without replacement and observing the color, that is not what you are. That is not what your question is not based on that. Okay, your question is based on, and it's not even based on what I've just asked here. We are going to look at this later. It is. I was just asking you to just give me the probability of obtaining a red ball. Just obtaining a red ball without reading so much. Okay, now let's not read so much into it. Okay, if you were to find the probability of finding the first ball to be red, what would it be?
That would be 4/6.
That would be 4/6. The second ball is red. What would that be?
4/6.
4/6.
The third ball, not the third ball. I mean, the first green ball
2 over
2 over
6.
6.
And then the second one.
Same
2
2
over
over
6.
6.
Was it 2 over 6? Yes, 2 over 6. And
Yes.
the second one is also 2 over 6, which is 1 over 3, isn't it?
Yes, please.
Yes.
Exactly. So that was the answers I was looking for.
Okay.
But now you get it, no problem.
Yeah.
Without bringing the width and without replacement into the picture. So you just write them down. So the first one is 2 over 3. Okay. That is P of R. The second one, which is P of R2, is also 2 over 3. And then the others are all 1/3 and 1/3. Without considering successive 2 ball without replacement, no, this was just probability question. That's why I took the first one. When I bring the conditional probability, you see it. So put these answers down. Okay. I will roll these answers as a way that you were learning. Because I didn't indicate, because you have the right. Ideally, I should have asked that you find this thing after I've listened to this first sentence. After I've just gone through this first sentence and then asked you those questions before we come to now drawing them successively. Okay, any question on this? Let's continue. From this experiment, I'm giving you a sample space here. Okay, I'm giving you a sample space, and the sample space I'm giving you are G1 and G2 for the green balls, G1 and R2 for the green and red balls, R1 and G2 for the red and green balls, and then R1 and R2 for the red balls. This is a sample. So in fact, these are all the possibilities that one can get. Okay? For both, this is now conditional. But again, if you look at this conditional, you might not get the full sense of why I have written it like this. But you should be able to get a full sense of why I've written it like this, because the definition of conditional probabilities are dependent. Do you remember the definition of conditional probability? Let's take, for example, oops. Okay, let's take here. I think we can get it here. Okay. Take, for example, the G1 and G2. I can define G1 and G2. That is a probability of G1. The probability that the first draw is a green and the second draw is a green. This is the same as the conditional probability of G2 given G1 multiplied by G1, the probability of G1. And this is what we normally call the intersection. Just remember, yeah, let me just go up, and then you remember this. You see this definition here, this conditional probability? Let me just highlight it here.
Yes.
So this conditional probability, watch here. The probability of an event E given C is the intersection of the E and C divided by the PC. Which means that the intersection here is the conditional probability of E given C. Do you agree with that? Do you agree with this?
Yes, sir.
Okay.
Yes.
So across multiple. Now this one here, this one is the probability of E intersection C. Now I will come back here. That is the G1. Oh, let me just go down. That is the G1, G2 here. So the probability of G1, G2 is the same thing. This very one, the intersection here, is the conditional probability of G2 giving G1 multiplied by the probability of G1. So another way of, and I didn't show it earlier there, but I'm saying that another way of writing the probability, if you want to write it properly here, another way of writing probability of A intersection B, another way of writing this is simply as a probability of AB. It's the same thing. So instead of writing the probability of AB here, in the previous one, the conditional probability formula that I gave you, okay, I did not write AB. Or in that one, I wrote E intersection C. Okay, the probability of E intersection C. But if we were to rewrite it in simple event terms, it's simply going to be probability of EC. So the probability of EC is the same as the probability of E intersection C, which is deductible from the conditional probability formula, because the conditional probability of A given B is the probability of A intersection B all over the probability of B. And therefore, when I cross multiply this very one here, okay, let me circle it. This very one here can be rewritten as probability of AB. Does that make sense? Before I'll let you do the other one. Does this make sense?
Oh,
Yes.
please, the probability of AB in expansion is the same as probability of A times probability of B, right?
The probability of AB is not the same as the probability of A times probability of B. It's the same in conditional probability terms. Is the probability of A given B multiplied by the probability of B. So what I mean is the probability of AB here is the probability of A given B multiplied by the probability of B. That's it.
Yes, please.
Which happens to be the same as this, isn't it?
Yes.
Intersection B. If you don't know, you write it down. So on the basis of this, you should be able to write for me. I've just given you G1 and G2. Okay. And that G1 and G2, remember, I'm not going to Bayesian. I'm just saying that G1 and G2 is the same as the probability of G1 intersection G2, which happens to be rewriting the conditional probability, which is the G2 given G1 multiplied by G1. Now watch carefully that G1 intersection G2 is the same as G2 intersection G1. You get me? The probability of A, B, okay, the probability of AB equals the probability of A given B multiplied by the probability of B. Okay, it is the probability of B given A multiplied by the probability of A. It's the same thing. You don't understand? I'll explain again. You do? Good. So this is what I want you to do now. If you do, I want you to now write for me, how would you write this? The probability of G1, I mean, in probability terms, okay? Because they are all part of the sample space. What would be G1? What would be probability of G1 R2? That's my question. Which happens to be the same as probability of G1 intersection R2. What would that be? Albert, let me ask you that.
Yeah, so it will be G1 given G.
Oh, take your time and write it up. Hey, G1. Take your time and write it first. So first of all, to be the same as well, bring the intersection first before you now give me the conditional spell.
So this will be G1 intersection R2, sorry. G1 intersection R2. which is in terms of conditional, it will be J1 given R2.
No, you didn't mention the probability.
Sorry, probability of J1 given R2 times R2.
Say it again.
J1 given R2.
Mention the probability again.
Sorry. The probability of J1 given R2 times R2. The probability times the probability of R2.
Say it again.
The probability of J1 given R2 times the probability of R2.
Are you sure that is correct?
Doc, can I try?
Yeah.
Okay, so it's going to be the probability of J1 intersection R2, which is equal to probability of R2 giving J1 multiplying the probability of J1.
Yeah. Okay. Is that what you had in mind, Albert?
Yeah, I completely missed the...
I don't know why you are mixing it like that.
Yeah, sorry.
Put that down. All of you should put that down. Before I come to the real question. Now, I want you to do the same thing for R1, G2. Jeffrey, I need you to give me the answer. What would that be? R1, G2.
G2 will be the same as probability of, the same as equals probability of R1 intersection G2.
Take your time. After you've taken your time, then you let me know that you're starting. Are you ready now?
Yes. No.
Okay.
So probability of
which one are you doing?
The probability of G.
Which one are you doing?
G2. R1 G2. Hey. R1 G2. Yes.
Okay. Right.
Is equals to probability of R1 intersection G2, which is equals to probability of R1 times probability of G2 given R1.
Good. That's correct. Albert, take us through the last one.
Okay. Write it down.
And these definitions you individually gave, you're going to find them. You're going to find for each one. So just be ready. That's where I'm going to now, because now there we are in a conditional world. Jeffrey, I'm waiting for you.
Sorry. So, okay. So the probability of so R1, R2 will be the probability of R1 intersection R2, which is also equal to the probability of R2 given R1 times the probability of R1.
Yeah, that's okay. But you can always mention the probability of R1 first before you multiply by the probability of R2 given R1. You know what I mean?
Yes. Yeah.
Just in the same manner, it would have been easier. All right. So now, what I want you to do, each one of you, is to now find these probabilities. Remember, now we have the conditions applied. Okay. So what I want you to, of course, when you find this, so the first question I want you to do is find the simple event probabilities here. Find G1, G2, R1, R2, G1, R2, and R1, G2. G1, you're finding G1, G2, R1, R2. Let me show you what you're finding. So this is what you're finding. You have all the necessary information I've given you. You know the balls that are there and everything. If you need further information, what I want you to do is to find these 4 different conditional probability items. These are in simple terms, but then it's the rearrangement of the conditional probability that has given us this. Where each one of this is talking about the intersections. You are going to find for each one of these. Emily, is it clear now before you finish and you said that you didn't know this?
Yes, Doc, it's clear.
Okay. So now, all of you find me the answers. There are 4 of them you are finding. They will require you to do some divisions and multiplications. And therefore, I'm giving you 10 minutes so that you have a fair time. 4, okay, 10, 12. So I'm giving you 12 minutes. Minutes. And then you send me the answers. Are you done? So, Emily, are you done?
No, Doc. So next.
So let's go back here. We are finding the probability that the second ball is green. Now remember, the second ball is green under the circumstance that we have a condition already now. The second ball is green. Yeah, who was talking?
Of myself, I was asking whether we will look at the combinations of all the events that will give.
Yes, you got to look over all the combinations, all the possibilities.
Okay.
And Emily put it right by saying that assuming certain things are in play. So you got to bring those certain things are in play. So how would you write this?
So it can be probability of G1, G2, or probability of
equals to what?
Is equals to probability of G1, G2, or probability of R1, G2, or probability of R1, G2.
Oh, you said R1, G2.
R1, G2 twice.
Yeah.
Oh, sorry.
He's right, isn't he?
Yes, Doc, is right.
So say it again. Okay.
Probability of G2 will be equals to probability of G1, G2, or
that all means what? That all is what symbol?
Addition.
Yes, so you should say plus.
Okay. Plus probability of R1 G2.
Yes. And don't say R1 G2 again.
Yes, please.
That's it. So this is the probability that the second ball is green. Can you all find this? Now that I've given you the formula, now that you have the formula, that's going to be your question 5. Find that and send me your answer.
No, so please, this without replacement.
Yeah, this as it is without replacement, yes.
What will change if it's with replacement?
It will not, the number will not, the sample size
calculation
will
for
not
them. The calculation for the P of GG and then P of R1 G2 will change. Like the figures will change if it's with.
Yes, if it's replacement.
Yeah, but everything we are doing is without replacement.
Yes, sir.
Okay.
Albert, are you with us?
Yes, Doc, I am.
You've got 4 minutes to give me the answer, all of it.
I don't know if my answer is correct, but
Well, you have to send it, then I'll mark you up or mark you down before I tell you.
I've sent it.
Okay, Jerry, you've sent me your way.
Yes.
Jerry, I need to save your number so that. Jerry, you sent me yours. Emily, you sent me yours. Albert, you sent me yours. Correct. I think you're all correct. Showing you the answers on the screen. So you should get something like this. That is the answer you all had. You all had 1/3, didn't you?
Yes, sir.
Good. So that shows that you're all getting the picture now. You see, this exercise is helping you now to understand what you're doing, are they not? Yes,
sir, it is.
Without the hands-on, you do not really think you know until you are challenged. So this is the probability that the second ball is green. Now, it doesn't end there. Because now we need to look at, now remember you can use decision trees to do this on your own. You can try that on your own and use decision diagrams to do that. Now let's look at another form of the condition, because I asked you the condition right now. What if the second ball is green? Now suppose the green ball was observed in the second draw. What is the conditional probability that the first ball was also green? You see that one? This is a very, very interesting question. Suppose the green ball was observed in the second draw. What is the conditional probability that the first ball was also green? So now we are not asking you the G1, G2, but we are asking you what? We are not asking you that intersection question, which is the one you just solved, isn't it? No,
Yes,
not.
sir.
We are asking you what? What mathematical question are we asking?
Okay. No, I think we are being asked what's the probability of having G1 if G2 is green.
Good.
Sorry, giving G2. Okay.
So you are being asked here to find the probability of G1 given G2. We haven't worked anything like that. Well, we've worked it, but it's here hiding somewhere, isn't it?
Yes, sir.
It's hiding somewhere in one of the family. So I want you to solve that. Everybody, you got, because we've already found it, I just need, in fact, you already have the answer somewhere. Because remember, you're going to use the conditional probability formula. What is going to be the numerator formula? And what is going to be the denominator formula?
No, I think the numerator is going to be.
Probability of G2.
Albert, go ahead.
No, wait. You said probability of what?
G2.
No, that would not be the numerator.
Probability of G1 intersection G2.
Now you are talking. Probability of G1 intersection G2. Divided by
probability of G2.
You got it. So now I want you to find that, everybody. And that's the last one for today. Can you send me that? By the way, Jerry, that question you called question 4, it is actually Q, it's actually I, it's actually V. It's V and not Q4. So this, what you're doing right now is question VI. Okay. Because if I were to go back to the first ones, you all flopped. I don't want to include that.
Thank you so much. But please, should we send this one to?
Yes, send this one. This is the last one. The VI, question 6. I mean 6. The VI. It's a very, very simple question, simple answer.
No, please, quick question.
Yeah.
It is the probability of G2 giving G1 the same as G1 giving G2?
No.
No. Okay. Please, how much time do we have left?
3 minutes. Actually, to be honest with you, I thought this question you had it somewhere. Actually, you've actually calculated. Yeah, you've calculated the first one, the numerator already. And you've also calculated the denominator. Okay, the denominator you haven't calculated. Oh no, the denominator you have.
Yes, that's the 1/3.
You already have the one. That was the one you just found some few minutes ago.
Yes.
Oh.
So
Charlie,
it's the numerator that we haven't done yet.
You have done the numerator. Believe you me. Go back to your I, one of them. You found it already.
So that one we did G2 giving G1.
You can do a manipulation.
This is G1. Okay.
Oh, so that was why you were asking. So if that was the answer to your question, then yes.
Okay.
The answer to your question is yes, in the sense that the probability of G1, G2 is the same as probability of G2, G1, if that's what you were asking. But the way you write the formula are different, but it would lead to the same answer. That's what I want to tell you.
So,
Please, respectfully, can you repeat what you said? That's equal to thing, that relationship.
I'm saying that the probability of gene 1, gene 2 is the same as the probability of gene 2, gene 1.
Okay.
But the arrangement is different because the probability of gene 1, gene 2 is actually the probability of gene 1 multiplied by the probability of gene 2 given gene 1. Okay?
Yes.
But the probability of, what do you call it?
G1, G2 will have G2.
No, that's what we just said. G1, G2. Okay. But now the probability of G2, G1 is going to be the probability of G2 multiplied by the probability of G1 given G2. And it is that second one you are going to use to find your next one, which I am saying is going to lead to the same thing, but just the way you arrange it.
Yes.
I mean, I wouldn't call it the right hand side. I wouldn't call it probability of gene 1 as it is in the previous one you did. I'll call it probability of gene 2 multiplied by the probability of gene 1 given gene 2. So it's just like if you had the answers to be whatever answer you be is going to swap, but you're going to get the same answer. That's what I'm saying.
Yes.
At the end of the
Not
day,
the same thing.
Yeah, you get the same thing. And now you should use that to do your substitution. But I'm waiting for you.
Yes, Doc. Sorry. Double checking with the conversation.
Okay, Jerry, you're giving me your answer. Are you sure that's your final answer, Jerry?
Please, I think the substitution, that was the answer the substitution you asked, and I finally wrote as my final
No, what I mean is that you sent me your final answer, haven't you? Okay, I got it. I got your final answer. Next person, Emily. Emily, you have sent me your final answer. Okay, and then finally, Jerry. Albert. Okay, good. So Albert, you got it correct. So it means that Albert, finally, you have 2 out of what? 6. 2 out of 6. Okay, I'm sending you your answer. Emily, you have 6 out of 6. You also got it right. Jerry, you missed the last one. That 1/3 is wrong. It's supposed to be 1/5.
No. Okay.
So you had 5 out of 6. You see, I asked you whether that is all. You said that's all, and that I'm talking too much. All right, so this is how it's supposed to be. Okay. You're supposed to get the numerator to be 230, and then the denominator to be 10/30. That will give you 1/5, which will eventually lead to 0.2. That is it. Now, this is for your homework. I want you to do yourself. Okay, find the probability that exactly one ball selected is green, and then the probability that at least one ball selected is green. These are very poignant. See, the first one is exactly one ball, and the next one is at least one ball. So you should do that yourself, and I'll collect it next week. Now, I'll send you the slide so you will see the questions and you will see this one. Now, this latter one, I want you to do it and submit it to me. Now, do you guys remember I did mention that Once in a blue moon, we will meet physically. Do you remember?
Yes,
Yes, sir.